Good morning. Good morning. Pardon? Yeah, don't pick them up yet. Yeah, because I still have a student that needs to take the test. So they're going to do it after class. So at the end of class, you can get them. Ooh, let's do that. All right, good morning. So I threw together real quick the grades for exam 3. What you see here is a chart that shows the 18 students that took the exam. And the gray is exam 3, the orange is what that student got on exam 2, and the blue is exam 1. So you can kind of like just look at a student and be like, how did they do on each of the 3 tests? It's in order from highest grade to lowest grade for exam 3. So the highest grade in exam 3 was a 102, and the lowest grade was a 51. We had 2 A's, 2 B's, 4 C's, 7 D's, 3 not passings. The class average on this exam was a 71.2, and these are the grades for the first 3 exams. Our class average on the first exam was an 80.4, right? And then the average went up on exam 2 to an 84.8, and then on this exam it dropped off pretty significantly to a 71, all right? And this is standard deviation, so 8, 10, and 13, that just measures how close together or far apart you are as a class. So you can see that there's starting to be some differences between the students that kind of are understanding versus the students who are struggling. So the bigger this number gets, the more spread out the students are. So yeah, that's it. I have the exams up here. I'm going to have you pick these up at the end of class, because I have one student who's going to take the test after class today, so I don't want the test floating around here while they're sitting there. I don't think it's fair, so just hang tight. Any questions about this? I tried to get those graded and everything just in case anyone was thinking about dropping the class. The last day to drop was on Friday, so you're kind of stuck with me now till the end. We good? Any questions? No? Okay, well with that, let's get going. Yes, I'm sorry. You should always do corrections. So I can keep doing things to inflate your grade, right? But as far as you in terms of getting better at test taking, and not you, I'm just saying specific, I don't want to start doing things like test corrections, things like that. In college level, there's no retakes, test corrections, things like that. You just kind of got to get that out of your mind. Like you come in, you take the test, you got to be ready that day. And that's just the nature of college. So the more I keep doing things to kind of like push your grades up, I don't think it's good for you long term. Like in Cal 2, there's no test corrections. There's no retakes. Does that make sense? So I think right now, because these 2 grades, I did offer it on a previous exam, right? Was it exam 1 where I offered bonus? Yeah. So since that's already been offered to you once already, and the grades are actually pretty good. The class average for the 3 tests is a 78, almost an 80 average on tests for the class. All right, so that's pretty good. I mean, that's almost a B, right? So no is the answer. You should do the corrections though, because you have a final exam coming. That final is comprehensive in some sense, so you should go back through, see what you missed, and then ask questions. Anything else? All right, so what are we doing today? We are continuing what we had done last time. That is, we were in 4.3, and we were trying to figure out how the derivative of a function will dictate the shape of a graph. And we said that if the derivative is positive, the graph's going to go up, it's going to increase. If the derivative is negative, it's going to go down, right? And then we said, all right, we can use that to figure out where we have local maximums and local minimums. And that was this first 4.3.1 and 4.3.2. And then we started talking about this, what does the second derivative tell you? And I said it has something to do with this thing called concavity. So the idea is that, and I showed you all this graph, the idea is that if we move across the graph here, let's see, if we look at this, in the red region on this graph, you can see that the graph looks like a frown, looks like part of a frown. And in the green, it looks like part of a smile, and then part of a frown, and then part of a smile again. Anywhere you have the green, that's called concave up. Anywhere you have the red, it's called concave down. And the second derivative is what tells you where that happens, all right? So I'm going to go right into a problem. We're going to just start with an example. And I'm going to pick one right from the book. And we're just going to pick, let's do an even problem. Let's do f of x equals, let's do this one, 4x cubed plus 3x squared minus 6x plus 1. All right, so we have this polynomial function. And what we want to do, there's going to be a list of things I want you to do here, all right? The first thing I want us to do, part A, is find where this function goes up and then where it goes down. We used that notation last time. Remember I used a little arrow there to say, hey, tell me where this function increases, tell me where this function decreases, all right? That's first thing. Second thing, I want us to find any local max and mins. So I want us to figure out what are the highest points on this graph and the lowest points, local max and mins. That we did last class, so that there's nothing new there. Part C and part D are going to be new. Part C, I want us to find where the original function f is concave up and where it's concave down. Now that's a lot of words to write, right? So I have an abbreviation for this that I'm going to use instead of writing concave up and concave down. I said concave up is like a smile, right? Concave down is like a frown. So what I'm going to do instead of this is I'm going to write this. Find where f is concave up and then where f is concave down. Does that notation make sense to you? So this first thing, the arrows mean where's the graph going up and where's it going down. This notation means where does it look like this and where does it look like this, all right? Okay, let's see, what next? Part D. Find any, now I haven't even used this word before, so I'm going to have to define it for you. Find any inflection points. So what are inflection points, right? I haven't defined what they are. So find any inflection points. What this means is find where the concavity changes. It can either go from a smile to a frown or a frown to a smile. It doesn't matter which way it goes, but anywhere that it changes would be an inflection point. I'm going to show you a picture of it first before I continue with this. So in this picture right here, right? This would be an inflection point. See where the frowns like just transitions into the smile, right? It's kind of hard to figure out where a smile becomes a frown, but there's some point here where it's no longer frowning and it starts to smile. Yeah? And that would be our inflection point. Whatever x value this occurs at would be our inflection point. And then here we go from a smile to a frown, that's an inflection point, and then here's another inflection point. So we want to be able to find those, all right? So do y'all remember I mean, I know you took a test and then you had a weekend. Do y'all remember how we do part A? Sorry, I feel like I've got to sneeze. Go ahead. What do you got? How do we do part A? Yes? Factor what? The original function?
Well, the derivative.
The derivative, yeah. So we take the derivative, right? And we figure out the critical numbers. We figure out where it's 0, we figure out where it's undefined. And then from that, we get those critical numbers. What do we do with those? That's the closed interval method that you just had a test on. This is new. You do what? You figure out, so you find these critical numbers, right? These places that make the derivative 0 and undefined, and then you don't plug them into anything. Not for this method. What do you, yes? Okay, so test points. So you have to draw a number line, put your points, and then you create test points. Yeah, I feel like I'm going to sneeze. Hold on. I hate that. Okay, so I'm just reminding you, we'll go through the example, all right? We'll go through the example. But we do first derivative, critical points, draw a number line, pick test points, plug those test points into the derivative. Remember I made y'all promise me 3 times. You told me that 3 times in a row. You plug test points into the derivative, right? And then from there, you'll be able to figure out where things go up and down. For concavity, we do the exact same thing, but with the second derivative instead of the first derivative, all right? So there's no real new technique here other than we're working with the second derivative as opposed to the first, all right? Y'all ready to get going on this? Oh, man. All right, so I'm going to need both derivatives, right? Do you want to just take them both now? Get both derivatives? I don't care. We can do them one at a time. You want both? It's a pretty easy function, yes? Polynomial. It should be easy to differentiate. So let's take our derivative. First derivative is equal to 12x squared plus 6x minus 6. And then the second derivative, so taking derivative of that derivative, would be 24x plus 6. Double check, because if you mess this up, everything else is gone, everything's over, right, at that point. Y'all agree with these derivatives? Okay, here we go. So I'm working on part A, right? I want to try and figure out where this function goes up and down. So what I'm going to do is I'm going to take the derivative, I'm going to set it, the first derivative, I'm going to set it equal to 0. So I want to find where is that derivative equal to 0. Then I also want to find out over here, where does the derivative not exist? Now I'm going to go ahead and do this one now. I don't have to worry about this. Why? Because what? Yeah, this is a quadratic. This is a polynomial. There's no problems with that function. It's defined everywhere. So there's never any issues with division by 0 or square roots of negative numbers. So it's a very well-behaved function. So I have no domain issues here. But I can figure out where it's equal to 0. And to do that, I take the quadratic function and I set it equal to 0. And hey, now you're back in college algebra. That's quadratic. And you try and, well, let's try and factor it. Can we get a GCF? 6? Just 6, right? Just 6 comes out. And that gives us at least a 2x squared plus x minus 1. And then I can divide 6 on both sides. And I get 2x squared plus x minus 1 equals 0 still, because 0 divided by 6 is 0. And then now there I can either use quadratic formula or I can factor, right? So you're all Cal 1 students, right? Hoping to go into Cal 2. You should be able to factor this, right? 2x, x, 1, 1, plus, minus, equals 0. Do y'all agree? That's our factoring. Set each factor equal to 0. And you get here x is 1/2, and here x is negative 1. You have 2 solutions to that. All right? Now what I'm going to do is I'm going to take this and I'm going to draw a number line. I'm not plugging these anywhere, right? That's a different method when we're on a closed interval. That's what we do. Here, I'm going to draw a number line. I'm going to plot these points, make sure that they're in the right order. That will create a natural partition of our number line into 3 regions, because I had two answers, right? So that creates 3 regions. And now what I do is I pick a test point in each of those regions. Any point that I want, anything I want, right? So over here, I'm going to pick -2. Between -1 and 1/2, I like the number 0. It's in there, right? And over here, I'm just going to pick 1. And what do you do with those test points? Where do you plug them in? Derivative, right? And what are we concerned about? When we plug those numbers in, we're concerned about whether or not our answer comes out to be positive or negative, right? If it's positive, that tells us that our original function is going up. And if it's negative, it tells us that our original function is going down. So I'll do this right here. So now I'm plugging in those test points. So I'm plugging in test points. So I plug in into the derivative, I plug -2. Into the derivative, I plug 0. Into the derivative, I plug 1. Do y'all see why plugging these numbers, like the -1 and the 1/2, right? These two numbers, why do I not plug those into the derivative? Where do they come from? Where do these two numbers come from?
They gave me 0.
Yeah, they gave me when the derivative was 0, right? So if you plug them in, you know you're going to get 0. And that tells you nothing. It just tells you that you have a flat tangent line. That doesn't tell you you're going up or down. That just tells you you're flat. So I need test points that are not where these points are to tell me the shape, if the function is going up or down. All right, so plug in. All right, this is kind of a pain in the ass, but we can plug in here. So if you plug in -2 in there, I'm not going to go through the work, right? Is that all right with you? It's just tedious. -2 goes into the derivative. Well, you know, I'll do the first one. 12 times -2 squared plus 6 times -2 minus 6. When you do that, you get a positive number, all right? Because you're going to get 4 here times 12 is 48. Then you're going to take away 12 and take away 6. It's going to be a positive number. And then you plug in 0. If you plug in 0, I can do that pretty easily. 0 here kills those, and then you still have -6. So that's a negative number. See, I don't care about the actual value of the number. I just care whether or not it's positive or negative. That's all I care about. And then when I plug in 1, I get positive. You must check each one of these. Do not assume that it's going to, like if you get the first one's positive, you can't say, oh, well, the next one's going to alternate to negative, then positive. It doesn't always work that way. You have to check each one. Good? Okay, now I'm going to come back over here to my table, and I'm going to put the conclusion of what I just did in here. When I plugged in -2, my derivative was what? Positive, which means the original function is doing what over here? Going up. So I'm going to put here the original function f here is going up here, right? And then at 0, the derivative was negative, which means my original function is going down here. And then here it was positive, right, when I went to the derivative, and that means my original function is going up. So if I were to graph this function right here, here's what I can tell you. It goes up, it gets to -1, comes down, it goes to 1/2, goes back up, right? I know that's the general shape of the graph. Good? All right. Part A, can we answer part A? Part A said, where is it going up and where is it going down, right? So I think here's my answer, finally. My answer. All right, where's the function going up? That's happening. We actually look at it like an interval. We look at the x-axis. So it's over here, this region here, all the way to the left, all the way till you get to -1. Everywhere to the left of -1, we're going up. And also from here over this way, we're going up as well. So the way I write that is -∞ to -1 union from 1/2 to infinity. I'm using interval notation to represent the purple. And then it's going down between -1.5. And my recommendation to you is to always just use parentheses here. Don't worry about brackets. I told you all that last time. Just the safe bet is to use parentheses. Yeah, I don't want to get too much more into that. All right, we have figured out where it's going up and down, all right? That's part A. Part B, I'm going to put B right here. What was part B asking? Find local max and mins, right? Okay, do we have any local maximums? Do you see a place where the graph goes up and then comes back down? Like a hilltop, right? It's going to have to go up and down. Where does that happen? At -1, right? At -1, I have a local max. So I have a local, I'm put L max, right, at x equals -1. Now, if I want to know the actual height of that hilltop, what would I do? If I want to know how high it was, what would I do with that -1? Plug it into the original function, right? And that would give you where you are. So I could do f of -1, and I would get an answer, right? I'm going to get an answer. If I plug -1 in here. Let's see, can we do it mentally? Can we do it in our heads? Let's see. -1 here gives me a what? -4. Okay, -1 here gives me 3. So -4 plus 3 is -1 so far. Okay, I have -1 here. -1 here, and then -6 is +6, right? And then +1. So that's 7. I think it comes out to be 6. Right? Put it all in there, you should get 6. Now, what about local minimum? Do we have a lowest? So does it ever go down and come back up? Yeah, right here, down and back up. It happens at 1/2. So I have a local minimum at x equals 1/2. And so if I wanted to know the value, I'd take that 1/2 and I'd plug it into the function, right? Now, that's not as easy to do, right? Like in your head, it's hard to plug 1/2 in here. So I'm going to wait on that. I'm going to use a computer to get the answer. But I mean, we could, on our calculators, get 0.5, 1/2, and then cube it, and then multiply by 4 and get an answer, right? All right, we have answered part A and part B. Now we're going to do part C and part D, which is the exact same procedure, but on the second derivative instead of the first. Ready? Remind me to get that answer, this one. I'm leaving that open right now as an open question. Okay, so for part C, trying to figure out where this thing is going, concave up and down. I'm trying to figure out the smiles and the frowns on this. So what I do is I take the second derivative.
It's -3/4, by the way.
This one? Okay, I'll put it in here. Thank you. -3/4. So I'm taking the second derivative, I'm setting it equal to 0, and then I'm also taking the second derivative, and I'm figuring out where it doesn't exist. And I'll start with this, because we have the same exact issue. The second derivative is this, and that's just a linear function, which is a well-defined function. It's never going to be undefined, so I can just throw that out. And then over here, I have to figure out where is 24 plus 6x equal to 0. And that's going to be pretty straightforward, right? It's a linear equation. So just subtract 6 on both sides and then divide both sides by 24. And that reduces -1/4, right? Hold on. I'm having one of those brain issues. Yeah, okay. -1/4. Got it? What do I do with that answer? Plug it into the second derivative. No? Yes? What do I do? Number line. Number line test points. Number line test points. So when I do it on number line, it now breaks the number line into 2 regions, right? Because I only have one place where the second derivative is 0. And so now I pick a test point, two of them. I'll pick one over here. How about -1? I'll pick one over here. How about +1? Or 0? What do y'all want? 0? Okay. And where am I going to plug those test points into? The second derivative, right? Because you're trying to figure out if it smiles or frowns. And the second derivative tells you if it smiles or frowns. So let's do that here. Right? We're plugging into the second derivative. So we go second derivative evaluated at -1. We do second derivative evaluated at 0. So if I plug -1 in here, I get a negative, right? And if I plug 0, I get a positive. And what does that tell us? The second derivative is negative over here. What does that tell us about the original function? Frowning, right? It's frowning. Not that it's going down, that it's frowning. All right? So this tells me my original function should be concave down over here. And then over here at 0, my second derivative is positive, which means my original function should be concave up. Concavity, frowns and smiles, tells you nothing about going up and down, all right? If I tell you that a function is frowning, you cannot tell me if it's going up or down. You can't. Because, you know, if you look at if you look at a frown, okay, the left side of the frown, the left side of the frown, you would be going up, wouldn't you? But if you're on the right side of the frown, you'd be going down, right? So it's not enough to just tell you a function's frowning. That doesn't give you enough information to tell you if it's going up or down. But it is still a frown as opposed to a smile. Okay, let's answer part C. So my answer for part C, I want to know where's the function concave up. Let me start with that. So where's this function concave up? We're going to look at it like an interval on the number line. Isn't that over here? That way? So to the right of -1/4, a -1/4. So from -1/4 on, forever. And then the function is concave down to the left of -1/4. Any questions on that? On your final exam, which is the next test that you're going to take, which is, we only have 6 class meetings left, including today. So after today, we only meet 5 more times, and then we have our final. So on our final, this is what I'm looking for in terms of an answer for these. It's these intervals where it's going up and down, or sorry, concave up, concave down. All right, part D. Do we have any inflection points? What are inflection points? What did I say? Anywhere we have a change in concavity, right? Anywhere you go from a frown to a smile or a smile to a frown. Do we have that ever?
Is that what -1/4 is?
Yeah, -1/4 is our inflection point because that is the point at which we go from a frown to a smile. So our inflection point is here. Do y'all see that the inflection point is kind of like what the local max and min used to be? Like in a local max, we're looking for up and down, right? And then for local min, we're looking for down and up. The inflection is like, doesn't care if it's down up or up down. It just says, do we have a change? So this is our inflection right here. So our inflection point, we have an inflection at x equals -1/4. And if we wanted to, we could actually figure out what the value of that is on our graph by plugging that number into the function, right? We could take f, the original function, and plug in -1/4. And we get an answer, which I'm now going to go to the computer, all right? Let's go to Desmos, and let's graph this thing. So 4x 4x cubed plus 3x squared plus 6x minus 6. Was that it? Minus 6. Oh, where did I get that from? Minus 6x plus 1. There we go. All right, let's take a look at this thing. You have all the yes?
On the test run collection points, are you going to want us to have like the actual coordinate of where we put that in?
On the test, good question. On the test, for inflection, the x-coordinate's fine. For local max and min, I want the actual point, because I want to know the highest and lowest. All right, let's see what's happening on this graph here. Let's see if all the information we have makes sense. Where did we say this function would be going up? From where to where? Where would it be going up? Negative infinity to where? Negative 1. So here's negative 1. Negative infinity to negative 1. Does it look like it's going up? Yes? And then where else is it going up, according to us? 1/2 to infinity. So here to the right, is it going up? Yes. Is it going down between these two? Yes? Okay. So far, it matches what we've got on our work, right? We had a local max. Where was our local max? Negative 1, 6, right? Where was our local min? 1/2, negative, was it 3/4? Here, let me click on this. There we go. Yep, negative 3/4. So there's our local min. Okay, the inflections are a little bit harder to see. We only have one inflection point, don't we? And it was at 1/4, or was it negative 1/4? Wait a minute, what? Negative 1/4? So I'm going to put in here negative 0.25, oops, 0.25, comma, f of negative 0.25. There it is. I had the computer put that point on there for us. Does that look to you like the point where the frown becomes the smile? Over here, this is a frown, right? This is all part of a frown? But there's this weird transition point where you no longer have a frown, you actually have a smile. Right? It's like, I'm hoping y'all are getting that. There's a sad face, right? Here's a happy face. If I put, well, let me do it this way. If I draw a happy face, right? That's where the frown becomes the smile. That's what we're looking for, is that point. Do y'all see it? Okay. So the calculus basically matches the picture. And you have to imagine that there was a point in time where you couldn't do this as easily as I just did, right? Just go to a website.